Yeah, let's get started. So, hey everyone, my name is Pavlo. I work at Lyft, and yeah, today I would like to talk about how to build scalable and multi-module architecture for apps that use Jetpack Compose. Right. So before I start, just a few words about me. So I am Google Developer Expert for Android. Also, I work on mobile infrastructure at Lyft as part of the client architecture team, and also recently I've been working on some mobile performance stuff. And yeah, let's talk about agenda of our talk. And agenda is pretty simple. So as you know, we have a lot of different technologies, patterns, and like buzzwords in Android industry, like Jetpack Compose, like multi-module apps, like API and implementation modules, navigation, and dependency injection, and finally client architecture. And it sometimes might be pretty frustrating, like how to combine all of these into some meaningful design and architecture so that when the application scales, uh, it can benefit from all of them without having some issues with productivity, build times, and overall development experience. And in this talk, we'll take a look how can we combine them all in some good fashion. And all of the concepts they can be and all the code from this talk can be found on GitHub in the multi-module movies project. So basically, this is a sample project that uses the movie DB API. Basically, it can show you the list of some movies. It supports some search, some movie details, and stuff like that. Yeah, just to show all the concepts that we are discussing in this talk. All right, but the viewer might ask, like, why would you even care about multi-module architecture? So, like, overall, what multi-module application is that you have a project, Android project, which has a bunch of Gradle modules, since it's multi-module, right? So why can't we just, put dependencies on those modules, like so that they will depend on each other, and like let's call it a day, right? So what's the problem, and why would we need a separate talk specifically for that? And the reason is that when we have a bad multi-module architecture, it can lead to some pretty big problems. So, for example, first of all, it might impact the developer productivity, and in particular, it can slow down build speed really quickly. And we will see in this talk why it happens and how we can attempt to fix it. And also, like when your code is coupled, when you have uncontrolled dependencies on your modules, like in your dependency graph is like looks like more like a neural net than something else. So yeah, it may make development process pretty hard, and like all the spaghetti relationships between modules may be really harmful, which is something that yeah, we must avoid. And I hope this talk will give some idea how to do it. All right, so when speaking of all this stuff that we just seen, I want to take a step back and to talk about one concept which is called application binary interface, or ABI. And when we will take a look at this, we will understand like why multi-module architecture matters. So let's say we have two modules in our application. So by modules, I mean like Gradle module. So we have module A, right? And we have module B. And module B depends on module A. So basically in module B, a Gradle build file, you have like dependencies section, you have like implementation tag, right? And inside of this, you will specify module A. So, and let's imagine that module A defines a bunch of like public classes, public objects, some public interfaces, and those interfaces and classes can have some public member properties and member functions. Also, we have like higher order functions or public constants. And as you can see, in all those cases, the keyword here is public. And why is that? Is because all those public entities inside of the module, it's public application binary interface, or ABI. And it means that in case of any change of those entities, for example, I will rename a class, or I will add some public property, or I will delete some public thing from the module. When you build the project next time, it will force all the modules that depend on module A, in this particular case, to be rebuilt as well. So basically, when you change some code inside of this module, it definitely should be like recompiled and rebuilt, right? But also, if its public application binary interface changes, all modules that depend on it should be also rebuilt, because the build system does not know if those public changes impact somehow this particular module or not. And maybe even like fun that module B cannot use. You might have cases that module B does not use any of those public fields, but it still will be forced to be rebuilt. And like why it happens, and like how those modules are being built. So let's imagine some example of a bad configuration. So let's say we have module A, and we have module B that depends on module A, and we have module C that depends on module B, but also module C depends on module A. And let's imagine some use case where we're doing a code modification in module A, which changes the application binary interface of module A. So what happens in this case when we hit the build button, right? Or like we type in a command for building the project. So first of all, we will build the module A, right? Because the code inside of this module has changed, and this means we need to build it. Then module B depends on module A, and since the module A changed some ABI stuff, right? Module B should be invalidated and rebuilt again, just to make sure like changes in module A does not impact any changes in module B. Next, since module C also depends on module A, it means that module C should be also rebuilt, right? But module C does not necessarily need, in all cases, to like depend on module A, but still it will be rebuilt. And in this case, after a single change, like in public binary interface of a module, we will have 3 modules that are being rebuilt, right? And moreover, let's imagine we have not only module C, but we have a bunch of different modules. And all of them, let's say, depend on module A. In this case, I mean, you can see it will like retrigger like the hell of the project, and like you won't have valid incremental builds, but just some constantly rebuilding modules. All right, so let's take a look at some example of a better configuration. So let's imagine that module C is not depending on module A anymore. So it depends only on module B. So what happens now? Let's say we again changing the public application binary interface in the module A, and we are hitting the build button. So first, module A is getting built, right? Because it has some changed code. Next, module B, since it depends on module A, it will also rebuild. However, this is it, actually, because module C should not be rebuilt because module B has not changed anything publicly, and none of the modules that module C depends on changed anything. And it means that we're actually good to go. And this is like the power of incremental builds, that every time we don't need to rebuild anything, because module C was built on the previous session, and Gradle has cache from it. And let's imagine that we have not only module C, but a bunch of other modules, like many more of them. And as you can see, like in this case, still we have only 2 modules that are being rebuilt and not all the rest. It means that like build speed will be much higher in this case. And yeah, this leads us to another concept. And when we have a feature, and when we split the feature into 2 Gradle modules, the API module and the implementation module. So for example, we have a feature API, right, which defines some like public interfaces for the feature itself, but it does not contain any implementation details, only those like public stuff that we can consider like valuable to consumers of those features. And feature implementation is like a more like heavier module, which has all the implementation details of this feature. Yeah, so this is like the point of the separation. Yeah, so yeah, as I mentioned, like the feature API, for example, since we're talking about Compose, basically what it needs to have is just like a composable function, right? So like an abstract composable function which will provide entry point to our app. And it will be inside of the feature entry interface. I mean, just because we need to make this composable function abstract. On the other hand, feature implementation will have some implementation, and it will implement the composable function, right? And you can have multiple classes like screen, I mean, any types of classes, and we can add them, remove them, but they will be just like a private part of this feature and not, exposed to consumers. And what happens basically when we have this separation of concerns, like all the rest of the world and like all the rest of the features in the app, they will depend only on feature API, right? On those thin interfaces that do not have any logic, like they're very lightweight, and like they're less likely to change, right? And when we do the code modification in the feature implementation module, it will not trigger anything, like, right? On the feature implementation module will be rebuilt, because like we assume that if this is like a feature, like we assume that we can often modify a feature. We have new business requirements, we have some bugs, stuff like that. And when we're like doing modifications to this feature, like debugging some stuff, we don't need to worry that like the half of the application will be rebuilt. Especially this matters when you have applications that consist of like hundreds of thousands of Gradle modules, which like can become like really huge mess, right? So this is the way like how we can prevent this. And overall, if we coming back to our sample application, which works with movies, so basically we have some app module, which is like a root module, like plain app Gradle module that is an entry point to the application itself. And it works with a bunch of features. Like, so we have movie search feature, which is separated on implementation API modules, movie details, which also separates in API and implementation, and also data, like data layer. And yeah, we'll see, consider each of them separately, yeah, but just to have a general concept. And as you can see, if you have dependencies on features, for example, movie search implementation on the left, right? So it depends on the API of movie details and data API, but not on the implementations, which means that changes in public binary interface of any implementation part, they do not trigger anything and do not impact anything. Right, but we need to define rules here. So we have three types of modules: feature module, library module, and injector module. So feature module we just discussed, this is something that can be separated into API and implementation. So the library module is like common, like below you can see this like red bar. So basically this is just like a simple Gradle modules that provide some common functions. I mean, we can have such modules. This won't harm to have a few of them. We just need to, I mean, depend on them smart and do not add them as a dependency to each of the part of the application. And then we have injector module. So injector module, it sets up dependency injection for the whole project. And in case of the majority of projects, it's like app module, right? The root entry point to the application, it depends on like all the rest of the application, and it can define some dependency injection rules for all of them. And it can, as this third rule, it can depend on implementation module. And moreover, if you have like all those feature implementation parts of features, only injector module is allowed to depend on implementations. All the rest of the application can depend only on feature APIs, which ensures that like changes in those implementation modules will not trigger like rebuild for half of the application. All right, so let's talk about feature module architecture, right? So like we define that feature consists of API and implementation, but like how do we implement it? And like how do we design all of it? So in order to discuss this topic, we need to focus on two topics. First of them is like navigation, and the second is dependency injection. Why navigation is so important? Because like actually this is the main purpose of feature entry like layer, right? The API layer of the feature. Because for example, if there's a feature that provides some UI, some screens, right? The only thing that we need to expose publicly is like how to enter this feature. For example, I'm in another part of application, so how to navigate to this feature. So we need to have some like lightweight API so that like we can trigger some function. Like next thing like will be already in this feature. So yeah, and this is the whole purpose of like navigation and stuff like that. And dependency injection also is important because like we need to define what public dependencies are provided by some feature module, right? By some feature, but also we need to make sure that API module does not have all the like details about like dependency injection components, implementation, stuff like that. We still need to keep it lightweight. And now we will discuss like those parts separately. So yeah, let's start with navigation. So generally, since we're talking about architecture, when we're speaking about architecture, implementation is not important. So we can use any of the navigation libraries, right? So it's not kind of specific to some of them. But for the purpose of the example, I'll just use a regular Jetpack Compose navigation library provided by Google. And just like let's quickly recap like how does it work for a general context. So we have this nav controller, which we use like remember nav controller function, which allows us to like go through different navigation destinations. And then we define like nav host composable function. And inside, we define a bunch of composable functions, which are actually entry points to different parts of the navigation graph, right? So in case of like movie search feature, we will have inside a movie search composable function. And we can also pass arguments. So for example, we can create a bunch of nav arguments and define the type, and then just similarly put them into those like composable function that will in turn, like when the user navigates to specific part of the navigation graph, it will just show another composable function and call it. Yeah, and eventually you can use a nav controller to navigate to different destinations. For example, in this case, we are navigating to the second screen and we are passing some argument, which is like movie ID, for example. Yeah, so that's nothing new here. That's just like the plain like usage of Compose navigation library. And let's see how we can use it for our purpose. So yeah, as we mentioned, we have a feature API module and we have feature implementation. So let's see what components should we implement in both of them. So the feature API, this like blue rectangle, it has a feature entry entity, which basically the only thing it has, abstract composable function. No implementation, just need to have a like function which is annotated with composable annotation so that we can enter the feature. And that's why we call it feature entry. And on the other hand, the yellow bar is like feature entry implementation. So basically, this is like a body of this composable function, and this is what like implementation of the feature looks like. So yeah, and so in order to implement this, actually, let's define some core entities, like core classes that are like parts of some, like abstract library that we'll be using for our project. So first, we'll have an interface which is called feature entry, and it will have property like feature road, which is basically defines like which direction do we navigate through the graph. Then we will have this composable function, similar to what Jetpack Compose navigation library has. It will be our custom one, but under the hood, it will use like the same composable function, lowercase, from the library itself. And inside, it will call what our like abstract composable function, which is also defined in this feature entry class. So basically, yeah, eventually, the whole purpose of this feature entry interface is to have some abstract function which is annotated with composable annotation. And also, you might see some weird class destinations, but basically it's pretty simple. It's a type alias for map, where the key is a class of a feature entry of any implementation of the feature entry, and the value is feature entry itself. And for example, this is how we can, for example, if we need some destination in our application, for example, we need to navigate to a specific class, to this specific feature. We can just specify the type of the feature we need, and then we can use it. We'll definitely discuss it later, but yeah, just for the explanation, what is this destinations is, right? So again, now when the core components are defined, let's implement some feature. So as you remember, we had a movie search feature, and on this screen we can see movie search API part. So in the API Gradle module of this feature, we are defining abstract class movie search entry, which implements the kind of a more like extends the feature entry interface. And it has like feature road stuff. Basically, this is like for navigation library to help it to navigate, to define the right destination for the feature. Then in the movie search implementation module, we have the movie search entry implementation class, which implements our movie search entry abstract class. And what you can see here, basically, it just implements this composable function. But the implementation of the composable function sits into the implementation module, right? And inside, it can call another movie search screen. We can pass their view model. Let's not discuss how we instantiate the view model for now. We'll come back to this later. And we have on show details, for example, when we're on the screen, we just shows the list of available movies. What if we want to see some details about movie? So user clicks on the item, and this means we need to navigate to another screen. So how do we do it? We use this destinations map, right, that we defined is a hash map of like feature entries. We use the find function that we defined, and we just pass the type of the feature entry that we want to navigate. So for example, movie details entry, it's some interface that is defined in the another Gradle module of a movie details API module, right? This is another entry, another API part of some other feature. And from that feature, we just like call the destination function, which just generates a string, which will be used by the navigation framework like, to navigate to that feature, which we can see here. But basically, the key part here is like we are finding those entries by specifying the type of the entry. Yeah, and now that we've done all the like setup for the feature, let's set up the overall navigation graph for the entire application. So this is part of the app Gradle module. So like root module, which is, if you remember, we call it injector in this case, right? So again, we are retrieving the destination, the movie search entry from the destinations, and we just set up a dependency, navigation graph here. So just using like almost like default API from the navigation library, but instead of like specifying values manually, we get everything from the movie search screen. And like we use it like this with movie search screen because, as you remember, we defined our custom composable lowercase function. Yes, so this is the way how we can call it from here. And basically, in this nav host, we can define a lot of entries for different features, and this is how like it sets up the navigation for the project overall. All right, we discussed how the navigation work. Let's discuss how the other part of the architecture approach work, which is like Dagger dependency injection. So we'll consider like overall there are like two primary solutions for the dependency injection. This is like Dagger and Hilt, which is based on Dagger. So we will not discuss like other solutions like Coin because in scalable projects and large projects, it's important to have static dependency graph validation because it might be frustrating. Like it's better to avoid crashes at runtime with static validation. So let's consider those. And there is a difference between them, but Hilt is still based on Dagger. So the difference lies in the fact is that when we define how different Dagger components depend on each other, there are multiple ways to specify such dependencies. So first of them is a subcomponents mechanism. In this way, the parent component, it knows about all of its children, right? And it defines them. On the other hand, with another mechanism, which is called component dependencies, it's kind of vice versa because like in this case, children specify their parents. And Hilt is based on the subcomponents mechanism, but in this case, like we will take a look further, it's not something that we can easily utilize with API and implementation modules, especially if you want our API module to be independent of Dagger and do not know anything about like how the dependencies are being instantiated. So yeah, we'll focus in this talk on pure Dagger with component dependencies mechanism because Hilt uses only subcomponents. You have no other choice. So all right, let's discuss like how component dependencies mechanism work overall. So let's say you have module A, like Gradle module, right? Yeah, sorry, don't be confused. Like so, in this context, like module is not Dagger module, but it's still Gradle module. So, for example, in module A, we have a component A, right, which has a list of dependencies that it provides, and we mark this with a component annotation so that we know that this is a Dagger component. In module B, on the other hand, we have component B, but for example, it needs to use some dependencies from component A. In this case, we specify that we depend on some other parent, which is component A. And this way we can get whatever like dependency graph we had with component A, and we can use it in component B. However, Dagger has another neat feature. So we can also consider another case. So let's say in another example, we have module A, which has an interface provider A, let's call it this way, which purpose is similar as in previous example, just to define the list of dependencies that like all the other components will be depend on and use in their graphs. However, as you can see, provider is a pure interface. It does not know anything about Dagger. On the other hand, we have component A, which is kind of like implements, or like more rather, it extends the functionality of provider A, which is like another interface. And this one is marked with component. And the neat feature here is that in module B, when we define the component B, in its dependencies, we specify provider A, but not component A. So basically, in module B, we can depend on something which is not related to Dagger like at all, just on a pure interface. And let's see how we can leverage this mechanism and like this neat feature of Dagger. So again, let's come back to our overall setup. We have a feature API and we have a feature implementation. So in feature API, we will have this like provider interface, which will define, it will be pure interface with no knowledge of Dagger at all, but it will just specify the list of types like dependencies that our feature provides. For example, if this is a data layer, it provides some repositories and stuff like that. But it will be like only interfaces without any knowledge of implementations. On the other hand, feature implementation will have the component, which is annotated with the component and which will use this stuff. So basically, now let's see how we can implement another feature. In this case, it's data feature. And it's also like interesting that by feature, we can understand not only like, some feature screens or like flows. For example, by feature, we can, in this case, consider anything that extends functionality of our app, right? So in case of data, it just adds functionality of like databases, network connection, like consuming APIs and stuff like that. And like basically providing the data, and like the user should not care like where do they get this data, either from network, the database. In this case, what we can do, we have a data API Gradle module, which defines only the interface, like data provider, and we just define like abstract, property, movies repository. So basically, this is a repository which will provide us some movies, and we don't care where it gets it from. Then in the data implementation, we'll just have, this data component, which implements this data provider interface. And what's also important, that we can also use a composition local, and we will see why do we need it. But basically, this will help us to provide this data provider in our composable functions, right? So again, when we want to use a data layer in the movie search implementation module, right? So this is the implementation module, but we need, since we are implementing the movie search screen or feature, we need to have source where we get this data from. This is here we are as a dependency, we specify a data provider. And as you remember, data provider is just an interface without any knowledge of Dagger. So since we defined it as a dependency, so when Dagger generates code, it will generate a class like Dagger movie search component, right? And since it has dependencies, it will generate a function so that you need to provide this data provider to the Dagger. But there's a question, like how do we provide it? And this is why we define the local data provider, like composition local. So basically, we can just get this composition local from as a like data provider, and we can just put it into our component. However, we need somewhere to provide this data provider, right? Because it will not like appear out from nowhere. So what we can do here, we're coming back to the application module, right? The root injector module of our application. And if you remember when we were setting up the nav host, as you can see here, we have a navigation host where we specify like navigation graph dependencies. We can wrap all of it with a composition local provider composable function, and we can provide our data provider, right? Let's for now omit the way how we instantiate data provider, but again, we will come back to it later in this talk. But yeah, this way we made a data provider available to all the features in our application. But all those features, they don't care about like where do you get this data from. They just like have interfaces of like repositories. And this is kind of like how can we implement the clean architecture approach in this way, right? So because this is what current architecture says about, like we're separating interfaces from the implementations. All right, and when coming back to the movie search implementation, when we were like providing this data provider, you might notice we have this function which is called injected view model. So basically, we have some function. We created our Dagger component, and like we get a view model from it. But what is injected view model actually is? So this is like a helper function. It works pretty similar as Hilt view model function works. But while Hilt instantiates all the components like automatically, in this case, we still need to, create this Dagger component, which is not very like complex task. But inside, it has just like a view model factory, which is called as a callback, and basically in the end you call a view model function, which is like composable function that, and we pass there the factory. And this view model function will make sure that view model scopes are tolerated, and that like all the benefits of the Android view model will be preserved here. All right, so we defined a bunch of like feature entries, right? Which are separated between API and implementation, but we still need to set up some dependency injection for them as well. So in this case, there will be another approach. So all of them will be singleton. And why is that? Because they're pretty simple classes, but they need to exist during the whole application lifecycle, because at any point in time, other features can, navigate to them. But this is fine because feature implementation and feature entry, like feature implementation itself, it does not hold any state. It has just a composable function, right? But composable function, like scope and like destruction of the like obsolete UI will be handled by the Jetpack Compose compiler, right? But so overall, the feature entry class is very lightweight, so it's pretty fine to have it as a singleton. And we need to have another module, a singleton module, which will like provide those feature entries to the application overall, so that we can later set up the dependency graph. So yeah, for example, in the movie search implementation module, we define a function which is like singleton, scoped as a singleton, and it provides the feature entry implementation from this particular feature into some map, right? We're using into map, and we're using like a Dagger annotation feature entry key, where we define that the key of this, like in this map, will be the class of the feature entry. And again, yeah. Next, it's a feature entry key is a custom annotation that we created using Dagger API. Yeah, so, and when we come back to the application module, the root injector module, we just can include all the different feature entry modules from different parts of the application and collect them all in the navigation module. And then in the root app component, which is like root Dagger component, like the entry point to the application, right? You can just add this navigation module, and all of those feature entries will be automatically generated and put inside of the destinations. And if you remember, we identified destinations earlier, which is like a type alias for a simple map, like hash map, where actually the key is the class of the feature entry, and the value is actual instance of the feature entry. And this is why this way we can provide this instance, and we can like navigate to some feature. All right, and it's still not we have still some things to fix. Another thing is providing like common dependencies. So yeah, this is like a bit another topic, but let's come back to the application module in Gradle, and let's see the app component, right? What if we want to provide some common dependencies to the entire dependency graph? For example, like application context, right? We cannot define this dependency in the app component. And why is that? Is because application module depends on all the rest of the modules of the app. However, those modules, they do not reference application module. So none of the modules in the app depends actually on the application module. So there is no way they can access the context from the app component because they don't have reference to it. So how can we deal with it? Yeah, so like in this graph, we can see that, for example, a component of a specific feature, it cannot access the app component because like the dependency direction is like in a different way. However, we can create, for example, a common another Gradle module, which will be like a library module, and we will have provider, and it will work pretty similarly, where the provider will be just an interface, which will be put into the common module, right? We also have a composition local for that, and we have a like common component, Dagger component, which implements this provider. And when we want to use like context, for example, right? We just like, for example, in the data implementation feature, like feature module, we just reference this common provider. And as you remember, common provider just a pure interface with only like proper abstract property context. Again, it does not know anything about Dagger. And again, in the application, we also can include this common provider. So like this in our like application module needs to depend on anything in the app. And when it depends on the common provider, it actually can give the instance of the application constants, application context to it. And again, similarly to the local data provider, how we provide it with a composition local, we can similarly, on the other side, provide a local common provider, also as a composition local. And again, we just wrap all the navigation host logic with the composition local providers. And then inside of some feature, similarly, we can use a common provider. For example, if during the initialization of any classes in some implementation module of any feature, if we need a context, we can just easily get it automatically from the common provider. It will be injected automatically. Right, so basically those were like the primary components of the app. So if you notice that like we've discussed different like bars and components of the architecture, and now they go together into a single diagram, which represents the structure of a single feature of the app. So let's just recap. So we have like horizontal lines, which represent like feature API and feature implementation. So the feature API is like a blue colored bars. Feature API, the only purpose, it's two purposes, right? First is provide an abstract entry to the feature, which is like an abstract composable function. And also another thing is like define some dependency providers. For example, if any other feature depends on it and wants some dependencies and some classes from this feature, we can provide it in an abstract way. While the yellow bars here will just like hold the implementation of all this stuff. On the other hand, if we consider all those like things horizontally, so we have different Dagger scopes. Like we have a singleton scope, which defines like all the feature entries. They're singletons because at any point in time, any other feature can navigate to some specific feature. But this is fine because those classes are pretty lightweight and like they don't hold state. They just hold a single composable function. This is fine. And basically we hold them as a singletons. On the other hand, we have feature scope stuff, for example, which is like which describes the dependencies that this feature instantiates and also provides, because all those dependencies are valid only while this feature lives. And when it dies, when it's out of the scope, yeah, they should be scoped, because like out of the scope, those things will not be available. And yeah, and again, this results in such architecture where we have injector module, we have feature modules, and in the bottom we have a library module. And when any feature module needs to depend on another feature, it will rather depend on the implementation, or on the API part, but not the implementation, while like reducing the overall load on the incremental build and overall on the like build system. So yeah, that's pretty much it. Thanks a lot for your attention. Yeah, and I'll be happy to answer any questions. Yeah, thank you.
Hey, thank you. That was a great presentation. Let's give it a couple of minutes for people to add questions to the Q&A. We already have 2 so far.
Yeah, sure. Probably I will share my screen because the first question. So we have one question in slide 78. What is provides? So let's go to slide 78. Let me share my screen back. Slide 78. Yeah. So yeah, this is the mechanism that is provided by the Jetpack Compose, which is called composition locals. So what composition locals means is that, for example, what if you want to, the easiest thing, I guess, would be like, let me think how to. Yeah, so basically, I would suggest just briefly to check the documentation, but overall it means that you can provide some things like implicitly from other parts of the application. So for example, the easiest way to get an instance of context in Jetpack Compose is use a local context dot current. Basically, you don't know where it's being initialized and where you get it, but it manages like the way of like having different instances that are initialized in different parts of the application, but managed in terms of like Jetpack Compose scope and like tree structure, so that like when it's out of this branch, this instance will not be available. Yeah, so overall, I would suggest just checking like this is a default Jetpack Compose API, so like it's not something that I've kind of like introduced, but I'm rather using this mechanism to provide some instances from different objects I'm using. I hope that makes sense.
Yeah, it did make sense. We have another question, which is, are there any unique differences between multi-module architecture for UI built with views versus compose?
Yeah, I think the differences are pretty, yeah, they're definitely differences because with composable stuff, the only entry like point to the feature is like composable function, which works in a declarative way, while with classic views you have either fragments or custom views which have callbacks. They have imperative style, so the dependency injection setup will be different. Again, here as you can see, we're using like composition locals because this is only like a Jetpack Compose specific stuff. But overall, I think Compose is a bit easier because yeah, it's possible just to define an entry point to any complex feature just with a single abstract function that is annotated with a composable function. While with fragment and views, I think it's much harder to do.
Okay, great. I just had a couple of questions myself. When you're using, what are things that are not good to provide with composition locale?
Oh yeah, that's a good question. So I think with composition locals, it's not about what you provide; it's about in which scope you provide it. So for example, if we saw like in the slides where we like provided all our like Dagger stuff in the root module application,
Right.
which will wrap the navigation graph, it means that they will be provided as singletons and they will live forever. So if in this case, if we will provide to such wider scope like instance of a single activity, in case we're using multiple activities, that will be a memory leak of context. Yeah, so definitely need to be careful about like in what scope you're providing things.
Okay, great. So I saw in one of your slides, you had an info module, and an API module, and for various features. So when someone is like building a feature and is going about creating the scaffolding, is there a way to be able to automate that? Is there a way to, like, when someone goes and builds these feature modules, like how do you also verify that it adheres to these rules? Because you don't want someone to, like, have one module depend on another, like that it shouldn't. But how do you enforce these rules?
Yeah, that's a very good question. So like I think it consists of two parts. So first, the simplest one would be just create some IntelliJ IDEA like Android Studio plugins that will generate structure correctly. But even in this case, you can, there is nothing that restricts you to depend one implementation to another implementation. I mean, overall, the easiest thing we might do, as in one of the previous talks today was mentioned, that there are some tools that uh, I implemented as Gradle plugins that you can filter modules by name and specify, like, for example, if this is an implementation module, it cannot depend on any module that has like impl suffix. Simple like that, or like yeah. And overall, we just need to make sure when we depend on something, we can have linters that will validate that this thing is like, for example, it's a feature entry, but not something like from internals of the feature. Yeah, so like definitely some tooling might be involved in this case.
Great, thank you. This is a very informative talk.